In our last lesson, we talked about logarithmic and exponential functions. Today, we're going to look at what their graphs look like. So we're going to start by looking at our parent graphs and then look at transformations of each of those. So remember that our most basic graph that we can look at is called our parent graph. And for our exponentials and logarithms, we also have a parent graph. However, it's a little bit different. So with our exponential, remember that means we have an exponent, but our exponent has to be the variable. And our logarithm is going to be the inverse of our exponential function. Now, what's different about these than some of our other parent graphs is notice that we have a second or another variable in each of those equations, which is b. And b is for our base. And your parent graph is going to be slightly different depending upon what your base is. However, they will be generally the same shape, and then also we'll be looking at a pattern for our key points. So let's go ahead and look at y equals 2 to the x. So like I said, we want a couple of key points. So usually we're going to use -1, 0, and 1. Now the thing to remember is when I plug in a negative into my exponent, remember that is going to make me take the reciprocal of my number, and so I end up with 1/2. Likewise, remember that anytime that we raise something to a power of 0, we will always get 1. And then obviously 2 to the first is just going to be 2. And so any exponential parent function is going to have these three key points: -1, 1 over our base, 0, 1, and then 1, whatever your base is. So if we were to graph that, let's just kind of get a general shape of what we're looking at. So I would have -1, 1/2, 0, 1, and then 1, 2. So notice that as we put in more and more negative numbers, we're going to get smaller and smaller and smaller fractions, which means that we're going to get closer and closer and closer to the x-axis. However, there isn't anything that we can plug in that's going to give us 0. So that means that we have a horizontal asymptote at y equals 0. Also notice that on the right hand side we are increasing, and we're increasing exponentially, which makes sense because it's an exponential function. But recall that the bigger that my base is, the quicker that my graph is going to rise. So if I had a base of 5, that's going to get bigger much faster than my base of 2. Now, likewise, let's go ahead and look at y equals log base 2 of x. Again, just to give us a general idea of what the shape of a logarithmic graph is. Now, remember that logarithms and exponentials are inverses of one another. And in our last lesson, we looked at how to find inverses. And when we find inverses, we switch our x's and y's. So that means that our inputs and our outputs are switching. So notice that when we plugged in -1, we get out 1/2 for our exponential. It's going to be the opposite for our logarithm. So when I plug in 1/2, I'm going to be getting out -1. Because we're plugging in the 1/2 into our x, so we're saying what exponent of base 2 gives me 1/2. Well, it's -1. And then again, if we plug in 1, we would say 2 to what exponent gives me 1? Well, that's going to be 0. And then if we plug in 2, we would be saying 2 to what exponent gives me 2? Well, that's going to be 1. So again, just plotting some points here. We have 1/2, -1, 1, 0, and 2, 1. So notice that this time we're still increasing, we're just not increasing as quickly. Also notice that instead of not being able to get out 0, this time that's switched to we're not able to plug in 0. So that means that we have a vertical asymptote at x equals 0. Because remember, all of our x's and our y's have changed, which includes that vertical asymptote. Alright, so when we're looking at our transformations, remember that these transformations are going to be pretty much the same with any of our functions. We have horizontal and vertical translations, and then we can either reflect things, and then we can also compress or stretch them. So if it's inside of our exponent, it's going to move it left and right. If it's down below, it's going to move it up and down. And then if it's an a value being multiplied to the front, that's what's going to stretch or compress it. The key thing to remember is if it's in our exponent, that's considered inside of the function. And so it will move it left and right, but it's going to move it the opposite direction of the sign. So let's go ahead and look at an example of this. So we have y equals -1/2 times 5 to the x minus 2. So y equals 5 to the x is going to be our base function. And because our parent function or base function switches every single time, I'm going to go ahead and start by just kind of looking at those first key points. So -1, 0, 1. We're going to get out 1/5, 1, and 5. So if we were to graph that, we would get something like this. So that's going to be our parent function. But notice that we have an a value this time, which means that that's going to affect the overall shape of our parent graph. So we're going to go ahead and look at that same table, but we want to look at what that a value is going to do to that table. So notice that my inputs are not going to change. I'm going to multiply each of our outputs by the -1/2. So I get -1/10, -1/2, and -5/2. So now, if we were to graph that, notice that our graph has been reflected and it's been compressed by 1/2. So then our final step is going to be to move each of those points to the right 2 units. Because it's inside my exponent, it's going to be the opposite direction of the sign, which is why we move right. So let's go ahead and find a couple of things. So notice that my asymptote did not change. Because we did not move it up or down, the horizontal asymptote is still going to be at 0. So we have a horizontal asymptote at y equals 0. And then, so remember that for our exponentials, we are allowed to plug in anything, which means that our domain is going to be all real numbers. What's going to be different is our range. So notice that normally our range is going to be y such that y is greater than 0. But because we've reflected our graph, it's going to be y such that y is less than 0. And do be careful because it does not get an equal to bar because I can't equal it since it is an asymptote. All right, next up, we want to look at a slightly different function. So this is still considered an exponential function, but this is called an exponential decay function. And this happens when our base is in between 0 and 1. So we're looking at something like 1/2, 0.4, some sort of fraction or decimal that's going to give us something that's in between 0 and 1. And basically what that does is it turns it from an increasing function to a decreasing function. And so let's go over here. So if we had, say, an example of f of x equals 1/2 to the x, notice that our base is still, when I plug in 1, I'm still going to get my base. But since my base is a fraction now, I'm going to get out a fraction. I still get 0, 1 like normal, but now when I plug in -1, when it flips it or gives me the reciprocal, it's actually going to give me a whole number like 2. So the more negative that we go, it's going to keep flipping it and then give us a bigger number, which is why you see it shooting off to the left this time at our negative numbers instead of on the right. Notice that we still have a horizontal asymptote at y equals 0. That does not change, but it is decreasing this time. So let's look at an example. So here we have y equals 2 to the 1/4 x plus 2 minus 3. So again, we want to look at our base function, which is going to be 1/4 to the x. So again, I'm going to plug in those key points, -1, 0, and 1. But this time when I plug in -1, it's going to give me the reciprocal of 1/4, which is going to be 4. And when I plug in 1, I'm going to get 1/4. So notice that our graph is decreasing. Again, we have an a value, so let's look at how that a value is going to affect our overall shape. Something to point out is, remember that because we have an exponent that has a variable in it, and by our order of operations, we have to take care of exponents first. We cannot multiply the 2 and the 1/4. So it's a really common mistake is that people want to go ahead and try and combine those and say that I only have 1/2 x to the x plus 2, but we can't do that because we have to do our exponent first. We don't know what our exponent is, so we can't do the multiplication yet. But once we start plugging in things, then we can do that multiplication. So our inputs are going to be the same, but our outputs are all going to be multiplied by 2. So notice that our graph has been stretched vertically to be up and away from our graph. So then our last step, notice that we have both a horizontal and a vertical translation. So we're going to be moving 2 units to the left, because it's the opposite of our plus sign, and 3 units down. So notice this time, since we do have a vertical shift, we've shifted down 3 spots. That means that our horizontal asymptote has also shifted down 3 spots. So this time we have a horizontal asymptote at y equals -3. So our domain is still going to be all real numbers, but this time our range is going to be y such that y is greater than -3. Since we didn't reflect it this time, it is greater than, but remember we can't put that equal to bar because it's an asymptote. Alright, moving on. We have our logarithmic transformations. So again, we still have those a's, h's, and k's. They're going to do pretty much the same thing. The only difference is we're starting with the logarithmic graph this time instead. So we're still looking at h's moving us left and right, but the opposite sign. Our k's, which are on the outside, are still going to move us up and down, and our a's are still going to be able to reflect or stretch or compress. So again, let's start by looking at our parent function. This is going to be y equals log base 10 of x. Now remember, this is our common log, so it would be perfectly okay if I just wrote log of x, because remember, that's an understood base of 10. But let's go ahead and write it there just so that we remember. So I have x's and I have y's. Now, normally we would plug in -1, 0, and 1 for our exponential, but remember that those are going to become our outputs now instead. So we would want to plug in 1 over our base, which is going to be 1/10, 1, and then whatever our base is. And then this time we'll get out -1, 0, and 1. If it's helpful, you can always make the exponential chart first and then just switch all of those values. Sometimes that's helpful to actually see the opposite and then switch it instead. So let's go ahead and graph that starting graph. And so we have something that looks like that. Again, remember, it's increasing, it's just not increasing as quickly, but this time we do have a vertical asymptote instead of a horizontal asymptote. So then we also have a value this time. So let's go ahead and look at how that might affect our values. Again, just like before, when we have an a value, it's not going to change our inputs. What it's going to do is change our outputs. So the 1, 0 stays the same because anything times 0 is just 0. But now I have 1/10 -3. And then 10, 3. So notice that it has stretched it up and away from our x-axis. So then our last step is going to be looking at our final transformation, which notice that because the +1 does not have a parentheses around it, that means that it is not inside of our logarithm, it's outside of our logarithm, which means that we're going to be moving everything up 1 spot. So that would be our final graph. So this time we have a vertical asymptote at x equals 0. So because we have a vertical asymptote, and remember that our x's and our y's have changed from our exponentials, notice that our x is what's going to be restricted this time. And it's going to be x such that x is greater than 0. And this time our range is what's going to be all real numbers. Now, just like with our exponential, sometimes we're going to have a base that is a fraction, which is okay. It is going to slightly change what our graph looks like, and let's go ahead and look at that.